In this video, I'll construct the rational numbers. So, let's start with the integers. Let's assume we know everything about it, right? So this is going to be the set of 0, 1, -1, 2, -2, so on, right? And I know how to add numbers in here, and I know how to multiply numbers in there. I don't know how to divide, because that's what the rational numbers are for, right? So how can I construct the rational numbers from that set, right? Well, let's look at an example of a rational number, 3 halves. What I can do is I just assign it to the pair 3 and 2. Right there is going to be the numerator. Right there is going to be the denominator, right? So let's say Q is going to be equal to the set of all AB for A and B and Z, right? That's not a good definition, right? Because if I had 6/4, that's going to be equal to 3 halves. I can simplify it. So how can I determine that these two are equal in the first place? Well, you cross multiply. 6 times 2 and 4 times 3, right? So I know that 4 times 3 is equal to 6 times 2, right? Because that's 12, that's 12. So the importance of that is that we can now define what it means for the pair AB to be equivalent to the pair XY, I'll call it, right? These two are going to be equal to, if I transfer it into the rational world, it's going to be A over B equals X over Y, right? Cross multiply it, so A times Y, B times X, so BX equals AY. So that's what we're going to have. That's our definition. This is our definition. So we define this as if AY equals BX, right? So that's how we define this equivalence relation. If they're equivalent, they have this property. Okay, so what's the purpose of doing this? Well, now, this has a couple properties that you may already know, is that AB is equivalent to AB. Pretty obvious. This is called reflexivity. Okay, now AB congruent to XY implies that XY is congruent to AB, right? So this is called symmetry. And another property is that if AB is congruent to MN and MN is congruent to XY, then AB is congruent to XY. This is called transitivity. Okay? So, basically what this is saying is that if I transvert this into the rational world, I get A over B equals A over B. Right here, I get that if A over B equals X over Y, then x over y equals a over b. Right here, if I transport it into the rational world, I get ab equals to m over n, and m over n equals to x over y, then a over b equals x over y. Now, in geometry, in my geometry class, we're learning this sort of thing, but not in general, like this. So, we have this definition, and it has those properties. What I'm going to do is I'm going to find a over b. I've been using this a while, but I'm going to define a over b to be the set of all CD congruent to AB. Okay? More specifically, the set of all CD congruent to AB such that C and D are in Z, are in the integers. So, what I'm going to define Q as, Q is going to be equal to the set of all A over B for A and B in the integers. So this eliminates the problem we had with simplifying, because if I do A over B, so if I do, for example, 1 over 3 and 1 over 6 and 2 over 6, these things are going to be the same thing, because if I look at all xy congruent to 2 over 6 and all the AB congruent to 1 over 3, it's obvious that these are going to be the same, right? All the things congruent to 2 over 6 is going to be the same thing as all the things congruent to 1 over 3, right? I should write it like this. If AB is congruent to 1, 3, and 1, 3 is congruent to 2, 6, right? Then AB is congruent to 2, 6, right? By transitivity. Okay, and if I had AB congruent to 2, 6, and 2, 6 is congruent to 1, 3, then I get that AB is congruent to 1, 3. This eliminates all of the problems we'd have if we didn't have the ability to simplify. But now that we're dealing with sets of all things that are simplified, we actually have rationals. And now, time to define addition and multiplication on it. So, we say A over B times C over D is simply going to be A times C over B times D, right? Now, if I instead did A over B plus C over D, what you get is AD plus CB over BD, right? And this comes from the fact that if you have AB plus CD, what I'm going to do is I'm going to multiply that by D on the top and bottom, so A times D over B times D. I'm going to multiply that by B on the top and bottom, right? And I get AD plus CB over BD, because they have a common denominator now. Okay, so this is the construction of the rationals, and it's pretty interesting.